So, good morning, welcome back. On day 7 of this course, we will talk about combustion models and numerical simulations. So, last week we also have got some experience with Cantera, which we can use for simple calculations. Simple means simple in geometry, but of course complex in other details. So we are not talking about fancy 3D calculations using direct numerical simulations or exascale computing. So here we focus on the basics. Most of this lecture follows this book here. It's a nice short book, gives you a nice and brief overview of this topic. So we will talk about fundamentals, mathematical model, reaction mechanism, homogeneous reaction system, laminar flames, and I will give you an example for turbulent reacting flow too. So we need to know some basics, of course. So definition, equation of state, mass balance, elementary global reactions. Most of this we have discussed already, coupling functions, stoichiometry, mixture fraction, thermodynamics. So this was discussed already in previous part of this lecture. But to give you again some overview, so when we talk about the SI unit mole, this is expressed by the Avogadro constant Na. So 6.0236 times 10 power of 23 molecules define 1 mole, or atoms. So we have mole fraction, number of moles of species I, so Ni, and so the total number of moles is the sum of the mole fractions here, and the mole fraction of species I is then the ratio of number of moles divided by the total number. We have the mean molar mass, which is the sum of mole fraction times mass of each species. We have the mass fraction, which is the part of the mass of species I of the total mass. And then there are several simple equations to yield each quantity from the others. We also have to consider mass density, which is mass divided by volume, or molar density concentration, so number of moles per volume, and also these quantities are related to each other. Concentration is also when we use the ideal gas equation of state, so pressure over RT. So, and of course density, then pressure times mean molar mass divided over gas constant and temperature. So if we want to perform numerical calculation of the system, so now I go a little bit more in detail compared to the part with Cantera, of course. So first of all, we need thermodynamical data or a thermodynamical model. Then we need kinetic data. If necessary, depending on the equation system we want to solve, we also need transport coefficients. And finally, we need the boundary conditions. And this altogether gives us our mathematical model. And then we can perform numerical simulation and get some results. So this here is, for example, then done by the solver of Cantera. So there we don't bother about the mathematical model. We have to take care that we get these data here. We have this YAML files where the mechanism is included, the thermodynamical data is included, and the transport coefficients for the specific setup is also included. Most of the work was done already by some others, and you normally can use it. But of course, you also can modify it if you want. So what is the background of these thermodynamical data? We talk about heat capacity, enthalpy, and entropy. And these quantities we need to know over a broad temperature range. We are talking about reacting flows. So we have change of several thousand Kelvin in temperature within our flame. And of course, we need to know the quantities at specific temperatures. And mostly you can find these data in so-called Janov tables. So you have 1, 2, 3, 4, 5 coefficients given there to calculate the heat capacity with this polynomial set up concerning or with respect to temperature. Then there is a 6th coefficient to calculate the enthalpy from together with the heat capacity we have here, and not given here. There's normally a 7th coefficient, and so we can yield also the entropy. And then it looks like this. So we have entropy here in red, enthalpy in blue, and heat capacity in black. So as a function of temperature over a very broad temperature range. For an ideal gas, the inner energy and the enthalpy are only a function of temperature. So this is what we have seen on the last slide. So we can calculate these quantities if we know the reference temperature or the quantity at the reference pressure, reference temperature, and this is normally 289.1.15 Kelvin. So these Janov tables I've mentioned gives us data for these so-called NASA polynomials we have seen before. So I said we need 7 values to calculate Cp, H, and S. And these you can find in these Janov tables. So you see here normally 14 values. So you have 7 for high temperature range and 7 for low temperature range. And the temperature range in total is normally given by 2 numbers here. So it's 300 to 5000 Kelvin. Within this temperature range, these thermodynamic data in polynomial form has been tested and are valid. And normally there's, or sometimes there's also a third number here, not given here. Means where you switch between high and low temperature case. So if this number is not given, so it depends on the code, it's normally 1000 Kelvin, sometimes also 1500 Kelvin. So as I said, the temperature where you separate between high and low temperature case is either a given in this table or defined by the code. So this was presented already from Professor Sahu, that the adiabatic flame temperature, of course, is an important quantity. And what we need to know is that the enthalpy of the unburned and the burnt mixture is identical. So this does not change. So it means the sum of mass fraction of species J times enthalpy of species J over all species is the same. And then we know, okay, the change of enthalpy from unburned to burned is related to this temperature change. We can calculate an iterative procedure. So we change temperature, get enthalpy. Okay, it's smaller or bigger than the unburned one, so we change temperature again. And so with an iterative procedure, we can calculate HB in a way that it's finally equal to HU, and this is only correct if we know the correct temperature here. So, and with this iterative procedure, this could be done with Cantera, gas EQs, for example. There are several tools available. So you can, then of course it depends how complex you do this, so how many species you involve here. What you see here in table for different flames. So H to air, we yield an adiabatic flame temperature of 2380 Kelvin. H to O2 without nitrogen, of course, we yield a much higher temperature, 3000 Kelvin. And here is an example for a classical hydrocarbon flame, 2222 Kelvin. So most hydrocarbons we know have a flame temperature in the range of 2100, 2200 Kelvin, plus minus, of course. So then we need to know some empirical laws to describe the transport coefficients. So we need to know the diffusion flux. We need to know the heat flux. And here we have the viscose part of the pressure tensor. I will explain it later with some general equations where we use it. But here we have the diffusivity, so we need to know this diffusion coefficient. So this is the sum of all different multi-component diffusion coefficients we have depending on our system. And here, of course, we also have a gradient diffusion flux due to temperature gradient. And here we have the heat flux, so we have heat conduction plus and diffusion flux times enthalpy. So the change of energy with respect to change of diffusion due to diffusion. This we have discussed already in the combustion kinetics part. So there is, of course, in general formulation of an elementary reaction R. So we have the educts here, the products here. So here we have the stoichiometric coefficient of each species, and here's the concentration of a species. So for this specific reaction, we sum up over all species. We know on the educt side, giving all species on the product side. That means H2 plus O2 gives water, for example. This is the general formulation of this. And then we need to know, of course, this reaction rate here. So for a set of elementary reaction, the change of concentration of species I here is, with time, is the sum over all reactions, and then the change of this specific concentration using this sum of reactions. And the reaction rate then is defined by this Arrhenius equation. So this we have discussed already in detail. So, and this is how this reaction mechanism looks like. Here we have a list like it's used by the programs I normally use. We have seen it in the AML file for Cantera. So we have the equation we are talking about, and then we have this 3 coefficients here for the Arrhenius equation. The difference here is, here we see only the forward reaction. The coefficients of the backwards reaction, that means OH plus O gives O2 plus H, can be calculated based on the thermodynamical parameters. So in the Cantera example we have discussed, also these coefficients were given for the backwards reaction. That's the only difference. Here we see only the forward direction, the backward coefficients for the backward reaction are calculated. In the Cantera example, for both reactions, forward and backward, the coefficients were given. So how can we analyze such a reaction mechanism? So we have seen it consists of hundreds, thousands of species, hundreds of equations. There are some tools for quasi-steady state assumption, partial equilibrium, to reduce some parameters. We have, of course, a simplification of a reaction mechanism. We can perform a sensitivity analysis, and we can perform a reaction flow analysis to get information what is really important. Again, we have hundreds of equations, thousands of species, but depending on the problem we are interested in, so is it a laminar flame or is it an ignition event at a specific temperature, is it a lean flame, is it a rich flame, often only very few reactions are important to know precisely, because they are dominating the chemistry, and the rest of the parameters we need just to know very rough. So here's an example. So we have species 1 reacts to species 2 with a specific reaction rate, and this reacts further to species 3. So we can write up the complex equation system here. So we can yield an exact solution for this simple example. So the concentration of species 1, 2, and 3 are calculated using this setup. So of course I do not go here into the details, but this is the exact solution. So species 1 is of course this simple exponential decay. Then here we have this intermediate product S2, which is formed in low quantities only, and only at the beginning a significant quantity is visible. And then we have this fast growth of species 3. And so what we see from this plot already, that this equation here, reaction rate, is much faster than this one. And this we can use for this so-called quasi-steady state assumption. So the temporal change of S2 with respect to time is nearly 0, because the second equation reaction rate is much faster. So, and then with some simple steps, so finally the concentration of species 3 at a given time depends only on the initial concentration of species 1 at the beginning. So this is of course much simpler than this term here. And when we plot this, so we can see here the same result. Of course here there are some slight differences, but nevertheless, so the two dominant species here, S1 and S3, are represented very well with this quasi-steady state assumption, where we use much easier equations to describe the system. Then we have so-called partial equilibrium. So here for H2 combustion at high temperatures, we can assume that these three important reactions are in equilibrium. That means that the forward reaction has the same reaction rate than the backward reaction. So these three of the whole set of reactions we have are in equilibrium. So then, okay, we know that reaction rate of forward reaction times the product of these two species here, concentration of these two species is equal to the reaction rate of the backward reaction times the concentration of these two species. So with some simple mathematics we can yield these equations here, and if we plot this, we see that the partial equilibrium we see here for the oxygen atom at a given height over the burner where we have high temperatures is nearly identical to the detailed mechanism. So for this detailed mechanism we have used 9 species and 37 elementary reactions. And for this assumption of the partial equilibrium, this part we have simplified with this assumption here. So there's at high temperatures, so a distance, given a distance or height above the burner, very good result. Of course, at lower temperatures, so below 1800 Kelvin. Thank you. There are big deviations, so this assumption is not valid, and this won't work. And if we assume total equilibrium, so finally H2 plus 1/2 O2 gives water is in equilibrium, this won't work. So this partial equilibrium at some specific temperatures can be used to simplify, for example, our mechanism. Another simplification is when we look at the time scales we consider. So we are talking about turbulent reacting flows. So we have our physical time scales, so convection, flow, transport, and so on. And then we have our chemical time scales. So we have a range of seconds. We have our slow chemistry. So for example, NO formation does not happen normally in the flame front, but later in the exhaust gas. Then we have these intermediate time scales, but we also have very fast time scales. So we can call this equilibrium chemistry. So if we want to calculate a turbulent flow, we can assume that these steps are much faster, so this we do not have to resolve anymore. So we can use skeletal mechanism and reduce mechanisms. So that this work, just for an introduction, so we have here the complex combustion. I think it was on, okay, I don't know which flame we have here, but you see comparison of a detailed mechanism and a quite simple 9-step mechanism. So instead of hundreds of equations, we have only 9. But you see for the examined pressures here, 40 atmosphere, 60 atmosphere, temperature and species mole fraction of NOx or NO, nitric oxide, where the focus was on this work. So can be presented quite good. for phi equal 1. However, for the lean mixtures, you see already some deviation. So if you have such a skeletal mechanism, you always have to take care that this is optimized for one specific configuration. There it may work, but you cannot use it at higher temperatures, pressures, or different mixture composition, or you have at least to check it. So we have seen these time scales, and now we are in the state space. So we have our system described by two variables, water and carbon dioxide. And so this is our equilibrium. So this is where the flame finally ends, if we have an adiabatic system. So we can start everywhere in the state space. The system finally follows these trajectories and end at this equilibrium position. So if we want to describe, for example, only the final value, we can use the assumption of an adiabatic flame temperature, for example, and then we get this value. We do not bother about how we come to this end. This is not what we are interested in. But of course, here we know these trajectories. So wherever we start in our state space with our complex system, we end finally at this equilibrium state. So if we, for example, neglect chemical dynamics, so mix is burn, very rough assumptions, well, we have only the very slow processes here. So with t larger than 5 milliseconds, but at the end we will also land here if we consider processes slower than 15 microseconds. So we also see a similar behavior. So we cover much more of our state space. And this we can optimize. So I don't go into the mathematical details here, but we finally yield a one-dimensional manifold. That means we yield this manifold here in the state space here of water and carbon dioxide. And this finally describes our total system. So instead of using hundreds of equations for each species, one elementary or one fundamental equation to solve the system, we just need to solve the equations for these two variables, and finally we can describe the whole system. So it means if we know water and carbon dioxide, we know the concentration of all other species too, here with respect also to time. So and this works quite good. Here you see an example for an laminar premix flat methane flame. So here we have the consumption of oxygen as a function of distance. Here we have the intermediate species O, oxygen, so atomic oxygen, and the product CO2. The lines are the result using a complex mechanism. So 40 species, around 40 species, 180 something reactions, and the comparison just with 3 progress variables yield from the simplification I have described here. So instead of 39 species, we just solve the equation for 3 progress variables, and finally get all the information we need. So of course, with respect to numerical costs, this is very helpful. So what can we do to analyze the reaction mechanism we have further? So one possibility is the so-called sensitivity analysis. So we have seen here our temporal change of each concentration as a function of time. This depends on the concentrations of each species and on the reaction rate of all the different reactions we have. So then we know, of course, so the concentration of CI depends on the initial concentration of these species. So, and then we can consider how sensitive is the concentration of each species with respect to the different reaction rates. So if we change a reaction rate here, how does this change the concentration at a given time, for example? So here, this we can see here in a mathematical way. So we are interested in how does this change here if we change the reaction rate. So this is an complex equation which I do not want to describe here today, but what is the outcome? Here we see it with a brute force method, so they do not have changed or solved this equation system here. We see here they have just changed the reaction rate of each equation by a factor of 5, or divided by a factor of 5. And then they have the flame velocity without modification divided by flame velocity with modification. And so you see these are the most sensitive reactions we have. As expected, my favorite equation, H plus O2 gives OH plus O. This is the important reaction. If I change this reaction rate, I, for example, here change the flame velocity drastically. So by a factor of 3. It's very important to know this precisely if I want to calculate the flame velocity. This reaction dominates everything. So, and then we have some other species which I also have to know precisely, but the rest of the set, 800, 140, 150 reactions, I don't know, need to know precisely if I want to calculate the flame velocity. Here I have to focus, are these numbers here okay? Then I can be confident that my outcome, the flame velocity, is calculated with quite sufficient uncertainty. I also can perform a reaction flow analysis. So we have talked about different reaction paths already. So how do I get information about at which condition which part is of importance? So we can also, we have here a table as an output of such an reaction flow analysis. So the percentage of contribution of reaction R to the formation of species S. So a simple setup, table over all reactions and all species. So, and here species 1 is formed by 20% from this reaction, and finally 78 from this reaction. So this we have then for each species. So here, for example, species S-1 is formed by 100% from this reaction. So this we can use to analyze it and get such an reaction flow diagram. So this we have discussed already. So when we combust methane in air, this is here the lean part. We can follow finally to a carbon monoxide here. So over formaldehyde. So this we have discussed already. And if we have a rich mixture, we can see the flame will follow this way. So this is an outcome of the reaction flow analysis. So this again helps us to consider, are all the reactions I have in my mechanism are really necessary to solve my system for the complex setup I have. So for example here, this is for the lean flame. So this part here is very important, and here you see only small errors. So this is not so important. This change, of course, if we have a rich flame, then chemistry mainly goes this way. So this is an outcome of such a reaction flow analysis. And this, for example, can be used. So if I want to simulate only a lean methane air flame, I can use a mechanism which neglects this part. But finally, my result would be with sufficient accuracy. So therefore, so this can be used to reduce your mechanism or to optimize your mechanism. So at the end of this fundamental part, of course, we have to talk about basic equations. So the equations of continuum mechanics, balance equation for mass and momentum, balance equations for energy and chemical species. So of course, these equations are combined. So if we release thermal energy, so chemically stored energy is transferred into thermal energy, we increase temperature, we decrease density, and this of course affects the momentum balance. So all the equations we have are coupled to each other. We have normally a closed set of ordinary differential equations. So if we look at the Navier-Stokes equations, so we can, or we are interested in a Boolong's quantity F in a time-independent control volume. And so that means we want to solve for this part here, the change of this quantity is a function of space and time. So we hear this equation here, that's more or less a general description. So how this is influenced, of course, we have a change by a flux through our surface here. The species is flowing into our system, flowing out of our systems. For example, we have change by a source term, our chemical reactions, for example, or heat loss due to radiation. We have changed by long-range processes. Okay, this is radiation. With this equation, we finally yield that this can be described by these two terms here. And if we now leave this general description and write it in a For an infinitesimally small volume, we see that the change of the quantity with respect to time plus the divergence of this flux here is equal to this source term and this long-range term. So this, of course, now is very theoretically. So we want to yield now the result. So this general equation we have seen before is now here written for mass conservation, conservation of species mass, momentum conservation, and energy conservation. So again, we have a change of quantity and time. We have the divergence of a flux. We have a source term, and we have a long-range term. So for the mass conservation, it's of course the change of density of time, and is there is a convective part, so is there flow into our volume or out of our volume. For this species mass, we have additionally the diffusion flux to consider, convection flux, diffusion flux, and then there is the source term, the chemical reactions. For the momentum conservation, there is a long-range force here, the gravity, for example, and so on. So all these equations are just yielded following this simple description here. So we need to know some further information to solve this setup. So we have this pressure tensor, and there we need to know this viscous part of the pressure tensor. So here we have the viscosity, and then okay, here gradient of velocity vector and so on. So finally this gives us the viscous part of the pressure tensor, and then Fick's law, the diffusion flux here is described by the diffusion due to an gradient of the mole fraction of species I, and here there's also diffusion flux due to an temperature gradient. So when we go to Fourier's law, heat flux, so this consists of conduction, the so-called Duffer effect, so heat flux due to a concentration gradient, and the diffusion finally, and this part here in the middle normally can be neglected. So the heat flux depends on heat conduction, and this change due to diffusion fluxes. So now we have all the information we need to know to solve our equation systems. So for this simple example, perfectly steered reactor, we have discussed this model already with Cantera. So we assume here that we have a homogeneous mixture at given initial conditions. So we know pressure, temperature, and mixture composition at the beginning. So we have a homogeneous system, so there are no spatial dependencies of our quantities. So all these parts are zero. So finally, we just have to describe the dependency with respect to time. So here we assume that we have a constant volume. So this change here is zero. The change of our concentration depends on the reaction rate we have, and then we have the change of temperature. So we have a change of pressure here, we have a constant volume system, and we have a change of temperature due to this energy release from the chemical equations. And finally, this is solved or closed with this ideal gas law. So this we have seen already with Cantera, so we can use this to calculate the system with respect to time. Here we have a lean hydrogen mixture, so we have hydrogen and oxygen at the beginning, and so then we, at a specific time, the system ignites and we heat our water here. The temperature rises up to 2200 something Kelvin. And we also see here some intermediate species. So O atom is, for example, visible, and so on. And this we can use, for example, to calculate ignition delay times. Here we determine the steepest gradient in the OH profile. And then following this tangent here, we define that this position here is our ignition delay time, and this can be used, for example, for plots like this. So the ignition delay time of hydrogen, ethylene, and propane for different initial temperatures are plotted here, and you see here in this high temperature range they follow more or less in this logarithmic plot a linear relation. So it's following this Arrhenius dependency we know already. This then can be used also for very complex systems. Here we have an octane flame, so isooctane flame with oxygen and nitrogen, and we see for a lot of different species here comparison of numerical results and experimental results, and of course we have here sufficient agreement of the outcome. So with a very simple numerical tool, so in nowadays we are talking about seconds, less than seconds to get the result. We can really examine very, very complex systems and get a lot of information to analyze our system quite fast. So the laminar premix flame we have already discussed with Cantera. So for example, for a burner, we have a flow of unburned gas, and then we have somewhere this flame front, and here we have the exhaust gases. So, and the position of the flame front, of course, depends on the outflow velocity and on the flame velocity of the flame. And the assumption is that we have dependency only in flow direction, so that all other gradients are zero. So we have again a one-dimensional system here. And so what we need to know, so the continuity equation can be integrated, so we see that the density of the system times the velocity does not change. So the burning velocity here, this SL, is an eigenvalue, and we can use different solvers finally to calculate the laminar flame. So we can use stationary solvers, we can use instationary solvers. It depends more or less on the system we want to examine. So what we see here again, okay, flow direction. So we have the unburned reactants here, which then are consumed in the flame front. We have intermediate species which are formed in the flame front and then are consumed again, and finally in the exhaust gas we have our product, and also we get this temperature profile. So this we have discussed already with Cantera in detail. The equation system, so we have our temporal dependency here, which is 0. So if we would use a stationary solver, we could put here always a 0. What I prefer is to use an instationary solver, and so then finally this here goes to 0. So at the end we reach the stationary solution. So and then here we have, in addition, for example, for the species, we also have, of course, to consider diffusion fluxes due to gradients here of the species along the spatial coordinate. We have to consider convection here. For the temperature equation, we have to consider heat flux here. So these are some additional terms compared to the 0D equation system for the spatial, for the homogeneous reactor. This, of course, is true. We have to know the boundary conditions, and for this laminar flame, that means we know precisely the inlet conditions. So we know temperature, mixture composition here very well. And we know, okay, at the end we reach the equilibrium condition. So all gradients go to 0. So we don't need to know the amount or the exact temperature at the end. So, but we know that temperature do not change anymore. So on this we can use at the boundary conditions for our equation system. So the input values are the exact values for mixture composition and temperature. And at the right side of our equation system, we use this boundary conditions. So, and so said, this is mainly used to calculate the laminar burning velocities. And here we see an example. So we have discussed this methane mechanism with, during the reaction flow analysis in detail. So we have part for lean flames, we have a part which is more dominant at rich flames. And here you see the outcome. So we have in C1 and in C2 mechanism. So if we only consider this C1 part and neglect every reactions where we have C2 species, so we see this works quite good in the lean part, and in the rich part we have large deviations. If we extend the mechanism using this C2 part, we can see we get much better results. So again, we talk for most mechanisms with our computers today here about seconds, maybe some minutes, but this is then maybe a problem of your initial conditions of so for example, we have seen it with Cantera. Of course, you need to know this dimension. So if you use here 5 meters and your flame is finally in 1 millimeter, the numerical system needs some time until it optimizes it. But if you start instead with 2 centimeters instead of 5 meters, you yield your solution much faster. But nevertheless, so we are talking about seconds today to yield this information here. And so this depends, of course, on the Mixture composition, so here it's the amount of methanol in air. So at the stoichiometric conditions we yield the maximum, and to leaner and richer mixtures we are going towards zero. Here we see this typical outcome of the Arrhenius dependency. So if we increase the temperature, we increase also the flame velocity. There's also a pressure dependency. Typically, the flame laminar burning velocity decreases with pressure. But of course, this is dominated more by kinetic effects. So it has to be considered in detail for the specific reaction system. So, and here you see the result for different species with a simple setup. So, based on the pioneer work of Jürgen Warnartz, so this led to several PhD theses. So, someone has to create a mechanism and so on. This takes years of work, what we see here. And finally, we use it today for calculations which need only seconds. So we have a little acceleration now with this setup based on the pioneer work of all the colleagues here. And also can be used to examine experimental flames. So here we have height above burner temperature for different flames. And this we can then compare with the numerical work, and you see here, of course, sufficient agreement for the different species as a function of height above the burner. At that point, I would like to have a break. When shall we continue? 11:20, perfect. Or do you have any questions at this moment? No? Okay, so thank you.